These are notes to yourself so that you can redo the experiment easily. Data, I call that the belly of the lab. That's where everything goes. I would expect to see in data, I would expect to see these categories. Of course, the first thing you'd expect to see, most likely, is the data table. Again, something you will generate. I would like you to think a little bit about the most logical way to present your data. Followed would be an uncertainty estimate. Some people call that an error analysis, but I think that's the wrong word. It's not that you make mistakes. It's not errors that you make. It's an uncertainty in your measurement. So I don't call it errors. I call it uncertainties. Calculations, charts, and graphs all go in that section. Data table, uncertainty, calculations, charts, and graphs. All that stuff goes in the data section. That's the belly of the lab. That's the main thing you're doing right there. Writing feverishly good. Now the next one, summary. Please keep in mind that's all it is. It just summarizes your results. That's all it does. An example, I suppose in your Physics 4 class you did an experiment where you measured the acceleration of gravity. You remember doing that lab? I don't know if you dropped an object and measured it electronically or what, but you did a lab where you measured the acceleration of gravity. In summary, you would simply write down, I measured the acceleration of gravity to be. And here's another thing that I get pretty excited about. I measured the acceleration of gravity, G experimental, to be 9.75 meters per second squared, plus or minus 0.5 meters per second squared. That an experimental number always has a tolerance. When you're quoting a number in summary, you quote the number that you measured, and you quote the tolerance. Always, always, always. You know what it means if you say if you wrote G equals 9.75 meters per second squared, do you know what that means? Do you know what that implies? That is absolutely perfect. There is no uncertainty at all. That is the absolute value for the acceleration of gravity if you do not put a plus or minus on there. And of course, you do not measure the exact. There is no such thing as an exact measurement. So here's one of the places where, given the opportunity, if you leave this off, if you write your number, your summarized number like this, crucifixion. I'm going to crucify this. Out comes the cross, the nails, the hammer. I'm going to crucify it. So put that down. I wish not to be crucified, therefore, in summary, I will never quote a number that does not have a tolerance. And that's all you do, ladies and gentlemen. Don't tell me anything else. Just tell me what you measured. Summary is just that. You summarize your results. In fact, ladies and gentlemen, if you want to know, I look first at when I'm grading I read your purpose statement, I go immediately to your summary statement. The purpose of this experiment was to determine the acceleration of gravity in the laboratory. And then I jump down there, I expect to see, I determined the acceleration of gravity in the laboratory to be 9.75 meters per second squared plus or minus 0.5 meters per second squared. That's all you write in summary. So always go back and address your purpose statement. Reread what you thought your purpose was for the experiment and tell me whether or not you accomplished it and what value you got. That's all you put in summary. Conclusion is where you begin to tell me what you thought of the lab. In particular, I'm looking at your suggestions to improve the quality of the measurement. Most of the time, the suggestions will be essentially spend more money on the equipment. I could do better if you had better quality equipment. Which I understand completely. Those of you that do go into a technical or a scientific specialty, very often at work you'll be given a comment like this. They'll say, let's just use gravity. They'll say, we need to know the acceleration of gravity. You go to the lab and get an acceleration for gravity and bring it back to me, the lab director, bring it back to me, bring the results back to me. And what they're really doing is they're expecting you to go down and do a quick and dirty experiment and get a fairly good, but still rough number. Then you say to the lab director, if this number is adequate, then fine. But if you want me to shrink this down, you're going to have to spend more money. It's up to the lab director to decide whether or not the number he has is adequate for his purposes, or does he want to spend the typically thousands and thousands of dollars to improve the technique and get it even more. But you never ever go to the most expensive experiment first. You never do that. You do the quick and dirty, you get your results and say, well, here's my results. I can improve this if you give me more money to spend on the experiment. And it's up to the boss to decide whether or not I need a more accurate number. So, in conclusion, that's basically what you're doing. You're saying, what would I need to do to improve my number? Okay, let me check my notes here. So we've talked about purpose, procedure, data, summary, and conclusion. Purpose, this is for you. This you derive. Procedure, notes to yourself. Data, we talked about the belly of the lab. Summary and conclusions. Funny, I said conclusion, whatever. Okay.
So how do you come up with the tolerance?
That's a really good question, and in a few moments I'll talk about that. There's two ways of coming up with a tolerance, what I might call an optimistic and a pessimistic way. One of the things, the pessimistic way, is to simply say, what is the tolerance on my least accurate number? If I'm measuring things, I measure three different things. Which one has the most inaccurate value? And if I'm measuring length plus or minus 10%, if my uncertainty on length is 10%, I would say my most uncertain measurement is off by 10%, therefore I'm going to put a tolerance on my measured value of 10%. That's a very pessimistic way of doing things, but that's one of the ways of determining. There's much more sophisticated ways that we'll be talking about in a few minutes.
So is our uncertainty estimate, is that for some difference? Is that what you're
Second.
The uncertainty estimate, is that for some difference? Is that what you're calling that?
No, generally speaking, you're not, well, let me check it. She said, is that the percent difference between what you measured and what's real? No, pretend like you have no idea what's real. When you make these measurements, pretend like you have no idea, at least until the very end. And let me tell you about that. No, the uncertainty is not the difference between that and what's real, but you quote your experimental value, and sometimes in conclusion you can say, well, the real value, G theoretical, is 9.8 meters per second squared. Notice that it falls well within my uncertainty range, and therefore my experiment went quite well. But this number is not the difference between these two numbers. This number evaluates how accurately you use your equipment. Go ahead.
So we're never going to do a percent error where we do the calculations and get a theoretical value and then compare it to our experimental value. We never are going to do a percent error then?
Not quite. At lab, I'll have a handout for you about that, but not quite that. It's more like I was just saying to her, whatever measurement you make, the least accuracy, the worst measurement you make, creates your uncertainty. So I measure this, plus or minus 10%, then plus or minus 10% on my answer. Okay. Oh, and the other thing is, I do think that the purpose statement is extremely important. So I'm hoping that you have a nice, beautiful purpose statement before you begin. You should have a good purpose statement for it. If there's any doubt in your mind, you are perfectly welcome, in fact, encouraged to ask me, say, this is what I think the purpose is. Am I correct? And if you are, I'll pat you on the head and say, great. And if you're not, I'll certainly tell you what a more accurate version of the purpose statement is. I don't want to just tell you, but I'm happy to confirm yours. I don't want to just tell you, but if you are incorrect, I will help you get the correct purpose statement before you do the experiment. There's no sense in doing any experiment if you don't have firmly in mind what the exact purpose is. So between now and the lab this afternoon, I do want you to think about the lab I'll be showing you and try to figure out what the purpose of this thing is. Have it in mind, have it written down, and ready to go. Okay, meanwhile, we got some more to do here. Procedures, data. Okay. What I would like to do right now is just show you what happens, and I think from that you'll kind of figure out what's going on, but after I show you what happens, then I'll go back and start talking about the purpose and the presentation of this particular laboratory, which I think will be helpful. Okay, it's a calorimetry lab. A calorimeter, to me, primarily is this cup here. That's a calorimeter. Now, it has a fibrous, in fact, I think even a phenolic ring, which holds it inside of a larger container, but the phenolic ring and the larger container don't count. The only thing that counts is just this. This is what I call a calorimeter cup. Okay. Do me a favor while I'm talking here. In that sink behind you, fill it about 1/3 full with room temperature water, please. I have some unknown metal here, some metal shot. Unknown aluminum shot. And I put that in a little ladle. I put that in a little ladle with some water. In a boiling pot. So in this ladle here, there is hot water and hot shot. Now what I'm going to try to do is I'm going to try to measure the specific heat of this, pretend like you don't know what it is, metal. Okay. This is a sample of unknown metal and you're asking to get the specific heat. So the way we're going to do that is to measure initial temperatures of the hot water shot, the calorimeter cup system, then take our hot stuff, pour it in there, get the final temperature, and I claim we should be able to determine the specific heat of the shot from that experiment. At the beginning of your data section, you might discuss a little bit of what's going on. That is, yeah, we don't need any of this. I'll start over here. That is, of course, you know, this is really conservation of energy, isn't it? Calorimetry is basically something loses heat, heat lost equals heat gain. So that's conservation of energy. Now, in the experiment, there are two things that lose heat. When we combine it together, there's two things that lose heat. What are they? Somebody said the shot, that was one. What's the other? The water. There's some hot water. So I'm going to put down MC delta T for the shot, hot shot H, hot shot, plus MC delta T for the hot water. Now, what gains heat?
The shot.
The water.
The water and the cup, that's right. MC delta T for the calorimeter cup plus MC delta T for the cool water. Our task is to measure everything necessary so that we can get the specific heat of the shot. And of course, you can see what we're going to have to measure. We're going to have to measure combined C for the hot shot. Well, I guess we could do the math right now, couldn't we? So C for the hot shot is going to be this term, minus this term divided by these two characters. Did everybody see that? This one, that one, take away that one, divide by these two. So we have MC delta T, our calorimeter cup, plus MC delta T, cool water, minus, what am I taking away this one? MC delta T, hot water, divide by what? These two.